Because it's the third time we've ever seen an interstellar object. And interstellar doesn't just mean Matthew McConaughey, it means something not from our solar system.
October 29th is the very day when 3I Atlas completely disappears behind our sun, and like Avi Loeb already predicted, this massive interstellar visitor might pull off a hidden maneuver that permanently traps it within our solar system for eternity. The official explanation calls it a passing comet. But the initial measurements tell a different story: a massive object stretching 20 kilometers across, carrying a staggering mass of 33 billion tons, yet showing virtually no non-gravitational acceleration, despite having violent outgassing. If Loeb's hypothesis proves correct, we'll have absolutely no ability to observe the decisive moment. What critical events will unfold during that excruciating solar blackout? And who will be proven right or wrong afterwards? Let's walk you through the basics. The mechanics of this solar conjunction are brutally simple. When Earth, Sun, and Comet form a straight line with the Sun sitting between us and the target, observation becomes impossible. For 3I Atlas, this geometry will lock into place on October 29, 2025. At that moment, the comet passes approximately 1.36 astronomical units from the Sun, just beyond Earth's orbital distance of 1.5 astronomical units. The angular separation becomes so small that the Sun's overwhelming brightness completely drowns out everything nearby. For context, trying to observe Atlas during this conjunction is like trying to spot a firefly hovering next to a stadium floodlight while standing on the opposite side of the stadium. No ground-based telescope on Earth can compensate for this. Now, this particular blackout carries an unprecedented weight because only two confirmed interstellar objects have ever been observed passing through our solar system: Oumuamua in 2017 and Comet Borisov in 2019. But 3I Atlas is different, potentially 20 kilometers across, making it orders of magnitude larger than its other predecessors. The 6-week observation runs from late October through early December, capturing the entire Perihelion passage. Astrometric tracking, spectral analysis, and even the basic brightness measurements all go dark. The only hope we have is to rely on solar observatories as backup plans. The Solar and Heliospheric Observatory, known as SOHO, has coronagraphs that can image the region around the Sun. But here lies a crushing limitation. SOHO's detection power hovers somewhere around magnitude 6 to 7, while Atlas during this conjunction will likely register between magnitude 10 and 12. That's far too faint to be spotted at all. The Parker Solar Probe offers another slim possibility. Its WISP camera could, in a sense, capture Atlas only if the geometry lines up perfectly. But mission planners calculated that Parker's closest approach to Atlas during the conjunction window will be roughly 30 million kilometers, pushing WISP beyond its sweet spot for detection. Some historical examples show just how devastating these watching gaps can be. In 1973, Comet Kohoutek, for instance, was predicted to become the comet of the century. When it entered solar conjunction before its closest approach, astronomers lost track of it for several weeks. When Kohoutek finally re-emerged, it had dramatically underperformed every prediction. That tiny gap meant scientists could never fully explain what happened. For 3I Atlas, the stakes are way beyond typical cometary observation. If there's even the slightest chance that Avi Loeb's idea holds water, the perihelion window would be the only moment when an orbital move would make any physical sense. The comet's speed at closest approach will be roughly 44 kilometers per second. At that blistering velocity and that specific distance, the energy needed for changing course drops to its absolute minimum. But that moment will play out in total darkness, hidden behind the Sun, 150 million kilometers away from us. But before we can understand what might happen at perihelion, we need to grapple with something that shouldn't even exist in the first place. The first estimated size of this comet left the astronomers speechless, measuring at 20 kilometers across. Think about it this way: if you dropped 3I Atlas next to Manhattan Island, it would stretch from the very bottom tip of Battery Park all the way up to Central Park, and then back down again, twice over. This isn't a normal interstellar pebble drifting through space. This is a mountain, absolutely screaming through the void at 70 kilometers per second. But here's the craziest part: population models in astronomy lean on something called power law distributions. Basically, small things vastly outnumber big things. This relationship has shown up in literally every astronomical population we've ever studied: asteroids, Kuiper belt objects, impact craters on planets, and even entire galaxies scattered across the universe. It's one of the most solid patterns in all of astronomy. When survey astronomers build models for interstellar object populations, they apply these same power laws. The Atlas survey runs for telescopes that scan the entire reachable sky every 24 to 48 hours. These systems are specifically built to catch fast-moving objects, anything that noticeably shifts position between back-to-back images. Given what these surveys can do, population models spit out crystal-clear predictions. For every single 20-kilometer interstellar object passing through the inner solar system, there should be roughly 10,000 objects in the 1 to 2 kilometer range floating around out there. The odds of finding a giant comet first, less than 1 in 8,000. Those are lottery-winning odds, or even worse. Yet the actual discovery record tells a different story. Oumuamua was less than a quarter of a kilometer in length. Tuai Borisov, roughly 1 kilometer across. Then Atlas, a jaw-dropping 20 kilometers, showing up without any warning, without the massive swarm of smaller bodies that should have announced its arrival. The Vera Rubin Observatory, which fired up full survey operations in early 2025, threw even more gasoline on this mystery fire. In just its first year running, Rubin logged over 6 million separate detections of moving objects. Yet when researchers combed through that absolutely massive database, hunting for objects with the extreme speeds that match interstellar origins, they found fewer than 30 candidates. After painstaking analysis, none were confirmed as genuinely interstellar except for Atlas itself. The expected population of small, faint interstellar visitors just isn't there. They don't exist where they should. For anyone tracking this weird stuff, Atlas size isn't just a surprising number on a spreadsheet. It's a clear violation of how we thought the universe worked. When Avi Loeb emphasized the 20-kilometer size in his arguments, he was not just pointing out an interesting factoid. He's highlighting a statistical impossibility that screams for an explanation, whether that explanation turns out to be natural or something we've never seen before. But the size isn't just what's keeping astronomers up at night. It's even more terrifying when you look at how this thing moves. 33 billion tons, that's what 3I Atlas weighs, based on its size and estimated density. Even the Great Pyramid of Giza, one of humanity's largest structures, weighs roughly 6 million tons. You'd need 5,500 Great Pyramids stacked together to equal Atlas mass. The raw kinetic energy packed into that much mass moving at 70 kilometers per second is capable of taking down any planets it bumps into. But the mass itself isn't what creates the head-scratching paradox. The first Atlas is actively outgassing, violently throwing material out into space at roughly 100 to 150 kilograms every single second. In basic physics, every action demands an equal and opposite reaction. When a comet shoots out gas, the core has to kick backward, creating what astronomers call non-gravitational acceleration, which we can call the rocket effect. This rocket effect is expected and well documented across hundreds of comets we've studied. But 3I Atlas, it shows virtually zero non-gravitational acceleration. The minor planet centers orbit calculations put an upper limit of roughly 1 meter per day squared on any non-gravitational force. For an object spewing gas as aggressively as a TLAS, that number is incredibly small. The physics simply don't balance out. Let us break down why this is so bizarre. Using the measured outgassing rate of 150 kilograms per second and a typical gas escape velocity of 500 meters per second, you can calculate the expected thrust force, roughly 75,000 newtons, about the same as a large commercial jet engine running at full blast continuously for months on end. Now divide that force by a TLAS's mass of 33 billion kilograms. The math says the resulting acceleration should clock in around 2.3 meters per day squared, clearly big enough to show up in the tracking data. Yet the actual measured upper limit sits below 1 meter per day squared, at least 2 to 3 times smaller than expected. Researchers ran Monte Carlo simulations in a bid to make these numbers work. The results came back brutally constraining. For the acceleration to stay below what we're seeing while keeping the detected outgassing, the core must either be extraordinarily massive, pushing density above 1,500 kilograms per cubic meter, or the outgassing must be almost perfectly balanced in all directions, with jets firing opposite each other and cancelling out. Another explanation for this demands even crazier fine-tuning. For outgassing to create zero net push, jets have to fire in exactly opposite directions with precisely matched thrust, or multiple jets need to arrange themselves geometrically to cancel out perfectly. Comet 67P, watched continuously by Rosetta for over 2 solid years, showed wild swings in jet activity as it rotated and different areas were activated and shut down. Nature, it turns out, rarely produces the kind of perfect balance Atlas would require. So from a pure engineering standpoint, if someone were actually designing an artificial object meant to look like a natural comet while keeping a specific trajectory locked in, perfectly balanced outgassing would be the ideal solution. Strategic placement of vents, controlled gas release, maybe even active feedback systems. All of this could create the convincing appearance of comet activity without the messy, inconvenient acceleration that would blow your cover. The mass and acceleration paradox remains completely unresolved. The numbers refuse to add up under normal assumptions, but they also don't definitively prove anything extraordinary. At least, not yet, but the whole nightmare doesn't stop with physics. The path this thing is taking through our solar system will leave you terrified. The flight path of 3I Atlas reads like someone carefully planned it on purpose. The flat geometric surface defined by Earth's orbit around the Sun, called the ecliptic plane, serves as the solar system's fundamental reference frame, its baseline coordinate system. Interstellar objects arriving from random directions in the galaxy should show absolutely no preference for lining up with the ecliptic, but that 10% assumes a genuinely random arrival. When you start piling additional unlikely features on top of that foundation, the odds multiply in deeply troubling ways. The planetary encounters make everything stranger. On October 3, 2025, 3I Atlas sweeps within 29 million kilometers of Mars, a distance that counts as a near miss. The path later brings it within dangerous striking distance of both Venus and Jupiter, stacking up a sequence of planetary flybys that you rarely see outside of carefully planned space missions. But here's the intriguing part. Every planetary flyby changes an object's speed and direction through something called gravitational assist. The same technique NASA uses to slingshot spacecraft through the solar system at insane velocities. For 3IATLAS, each planetary encounter presents a perfect opportunity for it to tweak its trajectory. The Mars flyby could nudge the comet's velocity by a few meters per second. The Venus encounter might toss in another small change. Individually, these kicks are almost insignificant, but they stack up pretty well. Think about spacecraft mission planning for a second. Consider the Cassini mission to Saturn. To actually reach Saturn with the rocket technology available back in 1997, NASA designed an elaborate trajectory that included flying by Venus twice, then swinging past Earth, then using Jupiter as the final boost, each encounter adding velocity and reshaping the path like a cosmic pinball game. That trajectory was carefully designed, calculated years in advance down to the minute, with backup plans for every possible problem. Now think about 3I Atlas threading through multiple planetary encounters in the weeks right before its critical perihelion window. If this trajectory were actually designed by some intelligent beings, it would really demonstrate an insane mission planning technique that matches our best interplanetary missions. If it's natural, then it leaves us with a remarkable cosmic coincidence that occurs maybe once in several thousand random interstellar passages. Well, the trajectory question does boil down to interpretation. The numbers are what they are: 5-degree tilt, multiple close planetary passes, optimal setup for a perihelion move. Whether those numbers represent the universe's dice rolling favorably or something else entirely depends on how much weight you're willing to give to stacked coincidences. But whether by coincidence or deliberate design, the path is absolutely real, and it leads straight to October 29th, the one point in space and time where all these geometric factors come crashing together. But the insane trajectory is just the beginning. When astronomers actually looked at what this thing looks like and what it's made of, the strangeness is simply unimaginable. The first images rolled in from Gemini South Observatory in Chile, and something immediately felt off. Instead of the usual comet appearance, the images showed something entirely different. A concentrated forward-facing glow dominated the side facing the Sun, a brightness pattern that fought against every standard correction astronomers threw at it. The forward glow actually got more intense as the comet pushed closer to the Sun, before gradually fading out. By early October, the weird object had settled into a more normal appearance with a proper tail. As visual observations kept rolling in, chemical analysis added shocking new layers to the mystery. The James Webb Space Telescope, the most powerful infrared observatory humanity ever put in space, captured Atlas during a narrow observation window on September 21, 2025, right before the comet moved too close to the Sun for JWST's strict pointing safety rules. The NIRSPEC instrument recorded carbon dioxide outpacing water by a staggering 8-to-1. Here's why that ratio is so shocking. Every single comet we've thoroughly studied in our solar system shows water as the king volatile, typically beating out carbon dioxide by factors of 10 to 100. Comet Halley, Comet Hale-Bopp, Comet 67P Churyumov-Gerasimenko, water dominates them all. A comet's 8-to-1 ratio of carbon dioxide to water points to the idea that it formed either in the most distant frozen reaches of a planetary system or in the deep freeze of interstellar space itself, where temperatures hover barely above absolute zero. Then the green emission surge hit. In late September, amateur astronomers using backyard telescopes started reporting a distinct, vivid green color spreading through Atlas's fuzzy cloud. Professional observatories jumped in and confirmed what everyone was seeing. Chemical analysis pinned down the source: diatomic carbon molecules and cyanogen, both lighting up under the Sun's harsh ultraviolet radiation like a cosmic neon sign. For most comets, green emission shows up and gets brighter as they barrel toward perihelion. When solar heating hits its absolute peak and molecule production rates climb through the roof. But for Atlas, though, it developed a strong, pronounced green color while still sitting over 2 astronomical units away from the Sun. Way earlier in its approach than typical comet behavior would ever predict. Each of these chemical anomalies can be hand-waved away with creative physics and special circumstances if you really want to. But when stacked together, they paint a portrait of something whose behavior actively fights against being stuffed into any single neat category. And all of this bizarre behavior is building toward one critical moment that will either explain everything or make the mystery infinitely deeper. October 29, 2025, 11:43 UTC, marks the exact moment when 3I Atlas hits its closest possible approach to the Sun, moving at nearly 44 kilometers per second, passing 1.36 astronomical units from our star's blazing center. At that moment, the comet will be absolutely screaming through space at 44 kilometers per second, fast enough to cross the entire distance from New York to Los Angeles in less than 2 minutes flat. This single moment is absolutely everything. There's this principle in orbital mechanics called the Oberth effect. It describes how velocity changes work most efficiently when you execute them at the highest possible speed. For 3I Atlas, screaming into perihelion on its current hyperbolic escape trajectory, the Oberth effect creates one narrow window for maximum efficiency. Miss that window, and you're talking about exponentially more energy required. To flip from its current hyperbolic orbit, the one that'll carry it straight back out to interstellar space, into a bound elliptical orbit that keeps it trapped in our solar system, requires slowing down its velocity relative to the Sun. Specifically, we're talking about a delta V of roughly 8 kilometers per second applied directly against its direction of motion. 8 kilometers per second might sound modest compared to its total blazing velocity of 44 kilometers per second, but that change represents an absolutely staggering amount of raw energy. Let's put those numbers in terms we can easily wrap our heads around. A Saturn V rocket, the most powerful rocket successfully flown in human history, delivered about 10 kilometers per second of delta V to the Apollo spacecraft heading to the Moon. That required literally millions of kilograms of fuel, multiple rocket stages, and engineering precision that pushed 1960s technology to its absolute breaking point. For Atlas, With its crushing 33 billion kilogram mass, achieving 8 kilometers per second of delta V would demand energy equivalent to roughly 450 megatons of TNT. That's roughly 9 times the apocalyptic yield of the largest nuclear weapon ever detonated, the Soviet Tsar bomber. For anyone who even slightly suspects Atlas might be something more than just another comet, October 29th represents both the best opportunity for executing a hidden maneuver and the most frustrating gap in observation possible. The universe couldn't have engineered a better scenario for keeping secrets if it tried. But when December rolls around and Atlas steps back into the light, the scientific community will be locked and loaded for answers, and that's when the real battle begins. Dr. Tom Statler, NASA's program scientist for the Near-Earth Object Observations Program, now draws the line in the sand. In his words, it looks like a comet. It does comet things. It very strongly resembles in just about every way the comets that we know. For Statler and the vast majority of the mainstream astronomy community, Atlas fits, even if imperfectly, inside the broad and genuinely messy category of natural comets. There are so many wild examples that establish clear precedent. Comets absolutely do not always behave predictably or follow the rules we'd prefer them to follow. The anomaly list for Atlas has grown disturbingly long, wildly unexpected size, massive sustained outgassing, nearly perfect ecliptical line trajectory, carefully sequenced planetary encounters, extreme carbon dioxide chemical ratio, unusual visual appearance, and early green emission timing that breaks the normal pattern. Not a single one of these individually proves anything remotely extraordinary. But when you stack them all together, side by side, they form an uncomfortable pattern that deserves way more than a casual dismissive shrug. Loeb argues strongly that the time for definitive final judgment is December and the months beyond, when post-perihelion data finally reveal whether anything measurably changed during that invisible solar passage. The scientific method might demand that claims be falsifiable and directly testable through observation. If orbital capture actually occurs, eccentricity will certainly drop. If the object shows signs of artificial modification, post-perihelion observations might reveal detectable changes in rotation state, brightness patterns, or chemical spectral fingerprints. As December rapidly approaches, different scientific camps are preparing their detailed cases, sharpening their arguments, and the universe itself is preparing to deliver its cold, impartial verdict. The debate will ultimately get settled not by rhetorical argumentation, political maneuvering, or passionate speeches, but by pure measurement. And when those measurements finally come in, your understanding of reality will get seriously challenged. The first critical post-perihelion observation window cracks open December 5th through 10th, 2025. Within 72 hours of the first detection, path analysts will compute preliminary path measurements. Post-perihelion, if natural gravity forces alone influenced Atlas, the expected stretch value should be roughly 2.98. Any stretch value measurements significantly outside that range would signal that something beyond simple gravity altered the path. By January 2026, sufficient data should pile up to definitively describe the perihelion path. If the stretch value remains above 1, the debate effectively ends. ATLAS is a natural visitor from beyond. But if eccentricity somehow drops below 1, everything changes instantly, absolutely everything. The March 2026 Jupiter encounter adds a second checkpoint. As Atlas approaches Jupiter, precise tracking can reveal whether the path changed during closest approach or remained consistent with natural forces. The international space community has already begun preliminary discussions about sending a spacecraft to meet Atlas if it remains in a bound path. ESA's Comet Interceptor mission could target Atlas if it settles into a reachable path within 5 to 10 years. Citizen science groups are already mobilizing for December. The International Astronomical Union's Minor Planets Center has coordinated with amateur watcher networks worldwide to ensure maximum coverage. Amateur astronomers with modest equipment can contribute useful brightness data if properly set up. Either way, December 2025 will be remembered in space history as the month when the mystery of 3I Atlas reached resolution or grows into an even deeper puzzle. Right now, 3I Atlas is somewhere behind the Sun, moving through the most critical phase of its journey, and no human eye can see it. No telescope, No spacecraft, no instrument we've built can penetrate the solar glare. We're blind precisely when we most need to see. The story of 3IATLAS captures everything that makes astronomy both thrilling and frustrating. The joy of discovery, the challenge of incomplete data, and the humbling reminder that the universe doesn't arrange itself for our watching convenience. The only certainty right now is uncertainty, and that uncertainty will persist until early December when Atlas steps back into view. Whatever happened during those 6 weeks of invisibility has already happened. We're just waiting for light to carry the information across space to our waiting instruments. In December, we'll know, or at least, we'll know more. And perhaps the most unsettling thing about this entire story is the forced patience, the unavoidable wait, the knowledge gap that no technology can close. The universe keeps its secrets well, and soon, it just might reveal one more